Okay, so thank you. I'm happy to be here. And so I originally wrote this presentation in 19, uh, 19, 2015, which was the 100th anniversary of General Relativity. And so my goal is for everyone to have a fundamental understanding, discuss special theory, the general theory, and applications. So courage as we go forward. This is some really heady stuff. Okay, so in 1905, Einstein had a miracle year. He published 5 papers dealing with 3 themes. The first was the photoelectric effect. And this is what he won the Nobel Prize for. He didn't win it for relativity because it was too controversial. So this was the first quantum phenomenon. And it's really an easy concept. When a photon of light hits a metal, it ejects an electron. And that's it. And solar panels work this way. CMOS CCD chips work this way. You know, photon of light hits your detector, the CMOS chip, an electron, and that causes electricity to flow and the information to be sent. And then he did the special theory of relativity, which it wasn't called, I was called later special theory. It's on the electrodynamics of moving bodies. That was the title of the paper. And the third thing he dealt with was what's called Brownian motion. And Professor Brown was a botanist, and he was studying pollen under the microscope, and it was suspended water, and the pollen kept moving; it wouldn't stop moving. And so this was the first evidence that molecules are in motion and stuff. And this has been applied to the kinetic theory of gases. So those are the 3 seminal papers that he published during this year. So I have a question. How old was Einstein when he formulated special relativity? Was he closer to this age on the left, a young man, or an older man here? So
The young guy.
the young guy. Okay, so right. So Einstein was 26 at the time, right? But most pictures you see of Einstein actually are an old man, not a young man. So a lot of people would think, the general public would think, oh yeah, it was an old man when he came up with this stuff. He wasn't. It's only 26. He was working at the Swiss Patent Office, and he worked there for 7 years. This amazed me. I thought it was only a couple of years or so. 7 years, that's a long time. And then he graduated from college. He didn't have a PhD. He was also married and had a son, Hans Albert. So a lot of people think, Einstein lived in a bubble. All he did was think about this stuff. He didn't. He had a real job. He had a wife. He was married. He had kids, so, he was just like the rest of us. And then I love this cartoon by the Far Side. Just, put Albert here. Hey, what's this, Albert? Physics equations? Do you enjoy your job here as a patent clerk, Albert? And that's exactly what he was doing. He was working at the Swiss Patent Office, and this is when he formulated special relativity while he was working at the patent office, and he was writing physics equations during work. So that's good, which would get you fired these days. Okay, so now there's a principle of Galilean relativity. Okay, and this is really interesting. So the natural state of motion is not to be at rest. A lot of times you think the natural state of motion is to be at rest, but the Earth is moving, okay? So you're moving in a straight line at uniform velocity. It takes a force to manifest a change in velocity, which is acceleration, okay? And physical description of any mechanical phenomenon looks the same in all inertial frames of reference. We'll talk about that. Now, this is from his Galileo Galilei's dialogue concerning the 2 chief world systems. This is what got him in trouble with the church. And this is a quote: shut yourself up in a cabin in some large ship, and with small flying animals, a large bowl with some fish in it, a bottle that empties drop by drop into a vessel. With the ship standing still, the animals fly at equal speeds at all sides. The The fish swim indifferently in all directions. The drop falls straight into the vessel. Now, if the ship proceeds at any speed, so long as the motion is uniform, you will not discover the least change in all the effects named, nor can you tell whether the ship is moving or standing still. And I actually experienced this. My wife and I were on a cruise during a solar eclipse expedition, and I was jet lagged, so I went to sleep, and the porthole was covered. So when I woke up, I put my feet on the bottom, and I just had socks on, and then I couldn't tell if the ship was moving. And then I remembered this, and I didn't open the blinds, and I said, I want to do this experiment. So I took a piece of paper, and I'm walking, and I'm throwing it up, and it's falling down. I'm running backwards, I'm running zigzag, I'm jumping up and down, I'm doing anything I can to try to figure out whether the ship is moving. Now I could feel the motor, the hum, because we were kind of on the lower decks of the ship, but I couldn't sense any motion. And so I opened up the blinds, and I look out, and we were moving. And I was just blown away. Oh my God, this Galileo's right. So next time you're on a cruise ship, try this. I mean, it's really amazing. You cannot tell that you were moving because the ship was moving in a straight line at constant speed. And that is equivalent to being standing still. You cannot tell the difference if you don't have any frame of reference where you can look outside and see the clouds in the distance, and you see that you're moving. So that was really an eye opener for me. So this is the principle of Galilean relativity. Okay.
So closer to home, Greg. It's like, well, not home necessarily, but when you're flying and
Yeah.
the steward or stewardess drops pours pours something into your glass,
Right.
you're moving at 600 knots, and
Yeah.
you know
Yeah, you're moving at 600 something miles an hour. Yeah, you got to be just under the 700, which is the speed of sound. Yeah, you're right. It doesn't fall on you; it falls straight down. Yeah, because you're at a constant. And if you shut the windows in an airplane, you really can't tell that, but you can a little more because you're kind of rocking back and forth, the turbulence and all that kind of.
yeah, if
But
you
on
hit
a
the
ship,
turbulence.
huh?
So wear those headsets that are noise canceling,
Yeah,
and if you're cruising and there's no turbulence, it's nice
yeah.
and smooth. You don't know.
It's not, yeah, you can't really tell that. Yeah, you can't really tell that you're moving. Yeah. So that's basically what principle of Galilean relativity is. If you're standing perfectly still, or if you're moving in a straight line at constant speed, everything is the same. The laws of physics, everything's the same. The drop empties drop by drop into the vessel. Just like you're saying, the stewardess pours, wine or soda into the glass, it doesn't miss it or anything. Yeah. Okay. So, frame of reference. So, let's define what a frame of reference is. Now, this is a technical term that's used, but it's your point of view or your perspective. Okay. So, the frame of reference consists of an observer, a bunch of instruments that can measure length, time, weight, etc., in the same state of motion. So, an inertial frame of reference is one that the motion is in a straight line at constant speed and not influenced by any external forces. Okay, so observers in different reference frames can use the instruments to measure things. So here's an example. So here's two frames of reference, okay, or two perspectives. So think of this as cars. This one's moving fast. So this is a Ferrari, and this is a Fiat. Okay, so the Ferrari's moving very quickly, and you have instruments where you can measure from the Fiat's frame of reference, you can measure how the Ferrari's doing, their speed, the weight, the length, okay, and vice versa. Okay, so that's what's happening here. So you're both moving relative to each other, okay? You're not still. So you're both moving relative. This one's moving faster than here. So think of the Ferrari moves faster than the Fiat, and you can measure each other's speed, length, and weight. Okay, so those are the three things that change. So the original paper, I mentioned that. So two postulates Einstein had is the laws of physics must be the same in all inertial frames of reference. So the laws of physics are the same here and here. Okay, so one person doesn't have different laws of physics because they're moving faster. Okay, that's what he's saying. The laws of physics are the same, no matter how fast you're moving. If you're on an airplane or if you're on the ground, the laws of physics are exactly the same. Okay, and then the speed of light in empty space is always the same value. Okay, so it's usually rounded off to 3 times 10 to the eighth, or it's 186,282 miles per second. Now that sounds fast. So I did the calculation. So if light could circle the Earth, it would circle it 7.5 times in 1 second. So 1,001. I just went 7.5 times around the Earth. Isn't that amazing? I mean, that's fast. But to the universe, that's slow because it takes light millions to billions of years to reach us from the far ends of the universe. So it's just mind blowing, But this is the speed of light, okay? And I didn't put slides on this because, but I'll mention it. In the 1800s, physicists thought that light needed a medium to move through, just like sound needs air, compression of air molecules to move through. So they thought light needed the same thing. So they called it the ether. So the light moved through the ether. And then Michelson-Morley did a famous experiment using an interferometer. We'll talk about what an interferometer is later, but they determined that there was no ether. It was very sensitive, and so now we know that light doesn't need a medium to travel through. It can travel in a vacuum in empty space. Okay. So a lot of lectures you'll hear that, but I left that out because it just adds more confusion. So there is no ether. Light can travel in empty space and doesn't need any medium. So two things here. So not everything in relativity is relative. Okay, not everything changes. So let's look at what remains the same and what changes. So what remains the same? The laws of physics for all observers in all reference frames. Okay, so we said that here. Okay, so the laws of physics are the same for these guys. The speed of light for all observers is the same. So a person in the Ferrari is going to measure light at 186,000 miles per second. So will the person in the Fiat in frame 1 and 2. They'll both measure the speed of light the same, okay? Total space-time distance is the same for all observers. So if here is 10 light years, this will be 10 light years too, okay? So the distance is exactly the same too, okay? Geometry of space-time is flat for all observers, and we'll talk more about the geometry of space-time. We get this general relativity, but the space is flat, okay? And then 1 meter and 1 second remain the same for each observer in their own frame of reference. So what is relative, okay? So observer in frame A is traveling, I should put 1 here and 2, but is traveling at 0.8 c, which is 80% the speed of light, measures time and space for an observer in B traveling at 0.95. Okay, so this one's traveling 95%. This one's traveling 80% the speed of light. So observer A measures observers B time as slower relative to A's in the direction of motion. Okay, observer A measures B's meter stick shorter relative to A's, and also their mass is heavier in the direction of motion. Okay, so these are the equations here. So the three things that are relative are time, mass, and length. Okay, so what's happening here? Since this person is traveling faster in frame 2, right? So if frame 1 measures the time in seconds for this person, they're going to say, oh, his time is slower than my time. If she measures his length, you're going to say this is shorter than mine. And then if she measures the person's weight, oh, his weight increased dramatically relative to mine. But if she were to jump on this one instantaneously, like a Star Trek transporter, right? She looks at the time here, she would see, oh no, 1 second is 1 second, 1 meter is 1 meter, and his weight hasn't changed. But if she were to jump back here and measure, you see what I'm saying? So, Eric, can you maybe elaborate on that a little bit? You there?
Yep, I'm here. My timing was a little poor. My wife was asking me a question. Could
Oh,
you
okay.
catch me up in the last 10 seconds?
Okay. All right. Well, so what I'm saying is the three things that change in relativity are time, mass, and length. Okay, so what's happening here is in frame one. All right, this one's traveling faster. Okay, this is 0.95 c. I got to change these to frame one and two instead of A and B. That's confusing. So this one's traveling faster, the Ferrari, and this is the Fiat. Okay, so she measures his time. Okay, with her instruments and says, "Oh my God, his time is slower than my time." Okay. And then she measures his length here and she says, oh, wow, his length is shorter than mine here. Say these are the exact same length. And then she measures his weight and says, oh my God, his weight's dramatically increased. But if she were to jump into his frame of reference, like with a Star Trek transporter beam, right? And she takes the measure, she says, oh no, time here is 1 second. The length is 1 meter and his weight is the same, it hasn't increased. See what I'm saying? But if she would have jumped back here and measures his time relative to her frame of reference, then she'd see his time slowed down, the length contracted, and the mass increased. So that's it. Okay, that's special relativity in a nutshell. But it's like counterintuitive because if you're traveling two cars and your watches are synchronized and all that, everything's going to be exactly the same. You got to be traveling near the speed of light for this. So what can you add to that, Eric, to try to make it clearer?
Sure. So the demonstrate, and by the way, I don't know if since I arrived, it's just 7:30, if Greg kind of warned y'all. He invited me to join in to be available to help out with some of this. So for those of you who don't know, I taught physics at the high school level, so lots of demonstrations. And so what I would encourage you to imagine in your mind, one of the demonstrations I did with my students to try to wrap your head around this, is if you imagine somebody standing in front of you and they have like a basket full of like little baseballs or frisbees, or I used pens because that's what we had. And every second they toss one to you. And so every second you're catching a pen or a ball. Now, if they start running away from you as fast as they can while still throwing those balls at you at a rate of once per second, each time they throw a ball, that ball has to travel a further distance to arrive at you. So while they're throwing the balls at a very consistent and let's pretend perfectly accurate one ball per second, you are no longer receiving them at a rate of one ball per second.
Right.
And what I'm going to ask is everybody give a thumbs up if that's cool. And if that's not clicking, if you're not quite sure, I'm going to request that you speak up now.
Yeah. I'll forever hold your peace.
Or forever be confused because I'm going to move
I'll
on.
forever be confused in this case. That's true.
And Greg, if I'm taking too long, feel free to shut me up. But
No, no, no. Eric
here,
gave an incredible lecture a few years ago on special relativity. So that's why I asked him to join because I know he knows this stuff really well and taught it. So
well,
it's
hearing
good to
nothing, I'm
have
going to
a
assume everybody
perspective.
clicked on that. So now I just the leap you need to make is the act of throwing a ball per second is a clock.
Right.
Right? So that is the information traveling from one location in space-time to another location in space-time. So if their clock ticks at a rate of 1 second per second, and
Right.
it transmits that information to you at the speed of light. The rate at which that object is moving away from you, that is the source of the time dilation, because those ticks, you're not seeing them, you're not receiving that information at the same rate that that information is being sent, right? There's a little bit of a delay there. And of course, the faster you go relative to the speed of light, the more extreme it gets, fairly asymptotic, right? Even up to like 25%, 50% the speed of light effect isn't that dramatic. It's definitely there, but it's really when you're going like 98% the speed of light that this becomes really extreme. And so the other example, if you want to Google this, it's called the photon clock. And the idea is you have two perfect mirrors with a one photon bouncing back and forth. And if you throw that mirror away from you or it's moving away from you, you can't perceive the speed of light going faster than the speed of light. Therefore, the photon has to use some of its available velocity to go horizontally, to go away from you. It can't just bounce back and forth at the speed of light. It has to now travel a diagonal path, which means it takes longer to get from one mirror to the other from your perspective. Hence, it appears that the clock has slowed down. And the last thing I'll say before shutting up so Greg can get back to things is the effect is the same for both observers, right? Because observer A sees observer B moving away, but observer B sees observer A moving away. And neither one of them is right or wrong. It's the essence of relativity. So they will both perceive each other's clocks to be ticking more slowly. And I'll stop talking there in case anybody has
All right.
questions. And Greg, it's your show, so
Anybody else
take
have
it
any
back.
questions? Like I
Well,
said,
I
this
would
is
offer
the
that
point to
using
stop.
that same type of illustration, the in the 20th century, the terminology for special relativity said that mass increased, but in fact, mass did not increase relative in a relativistic way. Momentum, the current way of preferred way of saying this is momentum increases
That's mass
relative
velocity. Yeah.
to the observer. Momentum is mass times velocity. And so that's the factor that's important here is that velocity, relative velocity, is affecting our perception of time, distance, and mass.
One mass, right. So any other questions? I know it's confusing, but just think of these three things, and if you look at the equations, if you're mathematically minded, you can kind of see it. If v approaches the speed of light, so if you're 3 times 10 to the 8th meters per second times 3 times 10 to the 8th, so say you're at the speed of light, this becomes the same. So that becomes 1. 1 minus 1 is 0. Square root of 0 is 0. So anything over 0 is undefined or infinite. So time would become infinite at like the event horizon of a black hole. So we'll talk about that. See? So this is how you can see time slowing down. And then same thing with mass. This will go to 0, so the mass becomes infinite. And here you can see that length, if this is 3 times 10 to the 8th, 3 times 10 to the 8th, square that, divides 1. 1 minus 1 is 0, square root of 0, so your length becomes 0, you know. So, so you can kind of see it maybe, from the math too. Okay.
So I do have a question for Eric now that you have the math up here. So I notice it's v squared, so that takes the direction out of it. So if the other person was coming towards you at some good fraction of the speed of light, this would say, you square v and you would still have time dilation, not
Oh,
time
yeah, you're right. If it's a
regression.
negative and you square it, becomes positive. Oh, good point. I didn't think of that.
So just question. So it was a good analogy with the light having to travel farther, but does the analogy kind of still work if they're traveling towards you, even though it should still be time dilation, I think.
So I'm going to defer to any folks here who know more on this. because I taught at the high school level and I didn't get that much into this math with my students. But my understanding is that we call it time dilation and length contraction, but really that's only half of the picture, as you're saying, is that we can also have, like, it will not only contract, but we can also expand, conversely, as you're saying. So one of the examples I gave my students was if you shine a flashlight at somebody and they run towards you fast enough, you will give them a sunburn because it would be blue shifted into the. Now,
Yeah.
when you actually do the math, you can't actually move that fast, but the principle is still useful, right? And if you run away from it fast enough, maybe you can get Wi-Fi from that flashlight, right? Because it'll red shift into the radio. So again, don't check the math on that. It won't actually work because it's not that extreme, but in principle, hopefully you get what I'm saying. So yes, if we take the example I gave earlier where you're throwing the balls at a rate of 1 second per second, if that person starts barreling towards you on a race car or something, you're going to receive those balls a little faster than the 1 second per second because each subsequent ball is traveling a shorter distance to arrive at you. They're still throwing them once per second, but the second ball has less distance to travel than the first ball, and the third ball has less distance to travel than the second ball, and et cetera, et cetera, et cetera. So you're going to very quickly get overwhelmed and piled.
Yeah. See,
Okay.
I tend to think of it one way, and then you can say vice versa because it's too confusing if you try to do it both ways. So just think, the faster you go, time goes slower, mass increases, and length contracts. So time gets shorter, length contracts, gets shorter, and no, time gets longer and slows down. So time slows down, length gets shorter, and mass increases. Okay, so that's the essence of it. Okay, so don't fight it. Just memorize that and let it coalesce in your consciousness, and hopefully, it'll make sense at some future time. All right.
I,
So everybody okay to move on from here, or what do you
I
think?
would offer this. There is a directionality, but it's not included in these formulae. These
Okay.
formulae remove directionality because of the ratio of squares. That's just to give you um, the value of the relativity, not the
Right.
direction of the relativity.
Okay.
Okay.
All
Thanks.
right. So everyone set? Can I move on? Okay. So twin paradox. So here's another example here. So if you're traveling 80% of the speed of light, okay, to a distant star, it takes you 7.5 years, and then you turn around and then you go back, and the distance is 10 light years here. Okay, the elapsed time is 12 and a half years. And then on the return trip, you can read this here. So the basics here is the twin and the rocket ship returns 10 years younger than the twin that remained on Earth. So if you want the fountain of youth, go 80% speed of light for 10 light years and come back, and you'll be 10 years younger. So that's really interesting. That's the twin paradigm. And you can plug these values into here to get the. So this is just simple high school algebra right here, but it's just seems very counterintuitive. But like I said, it's relative. He's moving 0.8 c. So the person on Earth looking at his the twins. Time in the spaceship, his time is dilated, his length is contracted, and his mass is increased. Now, if he were to jump into the spaceship, then everything would appear normal. The mass hasn't increased. The length is the same. 1 second is 1 second. But if you were to go back to Earth, then he'd see that time is slowed down, length is contracted, mass is increased. See that it's relative to the person's frame of reference that this happens. Okay, so that's the twin paradox. Okay, consequences. So we said space-time geometry is flat. All right. So all reference frame measure the same total space-time distance. I said that. I'm just basically repeating this. Length contraction, objects seen in the moving frame of reference appear shorter along their direction of motion. Time dilation, time intervals In the moving frames, the reference appears slow in the direction. And this is important too. There's no frame of reference in which light can be at rest. Okay, so that's important. So light is never at rest. It's always moving at c, the speed of light. Okay, so simultaneity is relative. You see a lot of cop shows, and the robbers are going to break into a bank vault, right? What's the first thing everyone does? They synchronize their watches, so that at 8:06 we do this. At 8:10 we're doing this. At 8:15 we're doing this. Now think about it. Since everyone has their own measure of time, right, in their own frame of reference, what happens simultaneously? What happens in one frame of reference will not occur simultaneously in another. See, so that's kind of makes some intuitive sense. Mass is relative. Okay. Mass approaches infinity as you approach the speed of light. That's why nothing can move faster than the speed of light. And then mass and energy are equivalent, and this is in the embodied in E equals mc squared. And I'll talk more about that in a bit. So here's the famous equation. This actually did not appear in the original 1905 paper. It was published as a supplement 2 months later. Okay. And then the faster an object moves, the greater its kinetic energy, the more the object's mass increases. As the object's velocity approaches the speed of light, it becomes infinite. So the speed of light represents an upper boundary to all physical processes. Okay. So study of inertia, physics test. Hey, Einstein, converting some of that mass into energy and getting it out of bed. See, I think of inertia is the ability, things in motion tend to stay in motion. I think of inertia as this. You know when that's why you put a seatbelt on, because if you had to put the brakes really fast in order to avoid hitting somebody, notice how the seatbelt grabs you and pushes you back, right? You would keep moving and go right through the windshield. And like I remember in college, I always had my backpack with my books in the passenger seat. And if I had to stop really quickly for the red light, I'd see the backpack go flying, on the thing. That's inertia. The backpack and the books had inertia. So when I stopped, they wanted to keep going, continue the motion, but they hit the end of the car and they stopped. See, so that's the way I think of inertia. Is there a better way of thinking of inertia, Eric? Or how do you describe inertia?
Hey,
Ooh.
excuse me, guys. You're only 1/3 the way through your slides, and you've already blown through half of your time.
All right. Well,
That's relativity in
we can
practice.
go all night.
Yeah,
All right,
thanks, John. I wasn't sure how much time was allotted here, so
An
1
hour,
hour.
an
all
hour
right.
including
Well, all right.
Q&A.
Let's just move.
Okay.
How do you describe inertia, Eric?
Ooh, before we do that, could I make a quick correction? I realize
Yeah,
it's going
sure.
to take more time, but so in my usage of the ball analogy, I oversimplified, I think, to the point of being incorrect in this particular case. So let me make a correction. When two objects are moving towards each other, or an observer is observing an object moving towards it at relativistic speeds, let's say, you do get the same relativistic effect, but I think I accidentally said that it would be like if time sped up or if length expanded rather than contracted, and that is not correct. And I think that's why the photon clock between the mirrors is probably more useful, because that diagonal path the photon has to travel to change distance from you, because when we're talking about relative velocity, really what we mean is a change in distance from the observer to the thing that is being observed. You will get the dilation and contraction effects, regardless of whether the thing is moving away from you or towards you. And I think I slipped into wave stuff with red and blue shift and got probably mixed things up a little bit. So I just want to correct that. It works whether it's towards you or away from you, but it's always a slowing down of the clock. It's always the length contraction. It's not the opposite, unlike blue shift. So I apologize for saying something misleading there.
Yeah, no, but thank you for the clarification with the clock. So that visual with having to the light beam still having to travel this longer diagonal path, even though it's coming towards you. That makes sense.
So how do you
That's
describe inertia, Eric? How do you teach inertia?
Oh, you're I have to think about that for a second because usually it's on like day 3 of a long build up to separate all these
Resistance
little details.
of
All right,
change in
we
motion.
can get back to that.
Yeah, so what I'll say
Okay.
is there's a difference between a mosquito hitting a truck and a truck hitting a mosquito. How about that?
Yeah. Okay.
So
So
inertia is the resistance of change of um, direction or speed.
okay, yeah. That's why the backpack keeps moving when you put on the brakes, you know. Okay, so what is special? So let me hear from people that are not as much in the know. So what is special about special theory of relativity? Why do we call it the special theory? What's special about it?
Let's just make that a rhetorical question, my friend. You're running out of time.
Okay, so what's special about it is, boy, I'm on a time limit here. Okay, so what's
Always.
special is it's a uniform state of motion in a straight line. Okay, so this is for all frames of reference, all moving frame of reference. So one that's accelerating. Okay, so all implies accelerating frames of reference, not only those in uniform motion. So the principle of equivalence. So Einstein determined that gravity and acceleration are indistinguishable or equivalent. Okay, and so the example that's always used is this elevator analogy. And I kind of find this confusing, actually. And so, what I like to think of principle of equivalence is this: an astronaut experiencing going up on a rocket experiences 2.5 times the force of gravity, right? So, this would be equivalent if gravity increased. If he was standing still, but gravity increased 2.5 times, and you kind of feel this when you're accelerated in a to a lesser degree when you're in a car and you push the pedal to the metal and you feel yourself being pushed back. You feel kind of pressure on your chest, and you really feel this if you're on a roller coaster. That's because you're accelerating and the gravity's increasing. So you really feel it on a roller coaster. And so as you're accelerating, you feel more gravity. That's why your chest and you scream to let the air out and equalize everything. But you know that's the idea that acceleration and gravity are one and the same thing. Okay, that's the cornerstone of the principle of equivalence. Now, Newtonian gravity, you've seen this in high school. Mass is mass directly proportional to the mass and inversely proportional to the square of the distance. That's the way Newton thought of gravity. And space and time are not absolute. So if gravity is not a force, then what is it? Okay. So Newton thought of gravity as a force. So Einstein's view of gravity is the geometric curvature of space-time. So you've all seen this diagram. Think of being on a trampoline. It bends around your mass, okay? So think of this as the fabric of space-time, okay? Space and also time's interwoven there too. And so you put a mass, or it could be energy, just pure energy, not just mass, but it's harder to think of just energy being there. So let's just say mass. Okay, so mass and energy are the same, equals mc squared. All right, but here you have a mass, so it bends the space-time around it. And remember, special relativity, space-time was flat. Remember? All right. So here it's actually curved. And then this is the big equation of general relativity. And the reason I put this on is just so that you can see the this part here represents the curvature of space-time, and this part here represents the mass energy. So this is saying mass causes curvature of space-time. That's basically what's that's saying here. Okay. And then I'm explaining it here. I want to move a little quicker. And this is something that
Oh, Greg?
next to nobody what?
Oh, do you mind if I jump in on something?
Yeah, sure.
I
What?
don't want to take up too much of your time. Could you go back to the slide that has the Newtonian concept?
Yeah.
Okay. Is it okay if I take 2 minutes on something?
Yeah, sure. No.
Okay. So one thing I want to convey, with Greg's permission, as what kind of one of the ways to fundamentally think about a difference between Newtonian gravitation and what I'll call Einsteinian gravitation or general relativity, it actually relates back to the much more succinct definition of inertia that somebody generously provided. If you think about it, we take that, the old experiment of dropping a light object and a heavy object off the leaning tower, and
Yeah.
we expect the heavy object to hit first, but it doesn't. They hit at the same time. And this would be true whether you're dropping a baseball or the moon directly towards the Earth. They will accelerate towards Earth at exactly the same rate.
Right.
That's weird if you think about it and if you look at the math here. And so let's think about this from an anthropomorphized perspective. How the hell does gravity know to pull so much harder on the more massive object, which has more inertia and therefore takes more force to change its rate of motion, also known as acceleration, right?
Oh, yeah.
If you're accelerating two things of different masses at the same rate, one of them needs a whole lot more force to do it, right? F equals ma. How does gravity know to perfectly scale itself to do that? And you can say, oh, well, Newtonian gravity says, well, the objects pull on each other, but it's like, okay, yeah, but it still feels a little weird. And here's where I'm going to say general relativity actually makes things simpler in a way by making them incredibly more complicated, but really simpler in a way because the explanation is much more elegant and straightforward. And this is Einstein's man on a roof thing into a degree, or man falling off of a roof, I should say, um, which is that the reason that gravity scales perfectly to accelerate objects of different masses at the exact same rate is because they're not accelerating. They are free floating. They are falling. They are not experiencing a force. If you knock the moon towards Earth, the moon will not feel it until it hits Earth, right? Which is also why we get into, well, is gravity really a force here, or is it kind of an illusion? If
Right.
you picture that those two objects of very different masses are not being accelerated by a force, but are instead floating, and you're the thing that's being accelerated towards them, suddenly the fact that they have different masses no longer matters. And
Oh,
that is one of the great insights and really useful explanation or explanatory abilities of general relativity is it makes that weirdly simple. You then have to wrap your mind around the fact that you are stuck on the windshield of the Earth, accelerating outward towards space, and somehow somebody in Australia getting accelerated in the opposite direction doesn't seem to mind this very much. And that's a whole other thing that I won't take up any more Greg's time with. But I
all
just
right.
wanted to draw some connections to that difference there.
All right. So this is the thing. So right here, this is mass and energy. This is how mass and energy curve space-time. Now this I find really interesting. David Hilbert, this was a mathematical genius. He invited Einstein to deliver a lecture, and over this on relativity, and he heard Einstein's lecture, and then during the summer he actually derived Einstein's equations all by himself. Okay, and and then they published it at the same time. Isn't that amazing? And Einstein freaked out because he thought he was going to get, duped and stuff. So, but Hilbert fully credited Einstein because he never came up with the concept of curved space time and all that, and he just basically did the math. Okay, and but he didn't have like Einstein said, imagination is more important than knowledge. Einstein had the imagination, curvature, space, time, and all that, and then Hilbert just did the math. But it's just absolutely amazing that that he came up with it, and we should call it the Einstein Hilbert theory of general relativity. I wouldn't have been so nice if I came up with it. It would have been Einstein-Shanus theory of general relativity. But so gravitational time dilation. So time would run slower in regions where gravity is stronger. Okay, so this is kind of similar to the thing. So just remember that gravity, where there's more gravity, time runs slower. Just remember that, okay? And this has been verified. Atomic clocks on airplanes that were 1 billionth of a second less, okay? And then gravitational time dilation. The GPS in your car, right, actually works using special and general relativity. You can read this here because the clocks run slower on Earth because there's more gravity. They don't run as they run faster because because there's less gravity up orbiting and everything else, but it wouldn't work unless relativity was taken into account. So people that say, so what practical uses general relativity and special relativity? Well, your GPS wouldn't work. So when you want to get somewhere, and you don't know where you're going on a map, you're actually using general and special relativity to do it. Now, proof of, let me go quicker here. So proof of relativity, orbital precession of Mercury, this given as a classic case. Newton predicts there's a difference between 43 seconds per century in the orbital precession. And, relativity accounted for this exactly. Precession is the orbit doesn't repeat exactly the same. It moves a little bit each time. So that little movement is 43 minutes per, is that minutes or no, seconds per century. Okay, and then the solar eclipse of May 29th was also used to confirm relativity. This was an actual picture of that eclipse. Look at that prominence. That's gorgeous. But so light was bent by 1.75 arc seconds. And then, of course, gravitational lensing that we've seen a lot of examples of from the Webb and the Hubble Space Telescope, and then black holes, the Schwarzschild radius. And Karl Schwarzschild came up with this equation while he was in the foxholes in the German army during World War I. Can you believe that? So he was writing physics equations while he wasn't being shot at in foxholes. Unbelievable, but he died a year later, unfortunately, due to an autoimmune disease he developed. But he figured out that the minimum for a stellar mass black hole needs to be about 3 solar masses. Okay, and then do black holes exist? Well, they could form from type 2 supernova, a massive star, and it'll either end up as a neutron star, or if it's 3 solar masses heavier, then it'll become a black hole. And then there's 2 types of black holes. There's the stellar mass, and then there's the supermassive black holes that are in the center of galaxies. Okay, now here's the black hole anatomy. Most of you are familiar with all of this. The singularity, the event horizon, and then spaghettification is really cool because my cat's over here. He came in. You'd feel more tidal forces at your feet than at your head, so you'd be stretched out. And the process is actually called spaghettification. Okay, and then in M87, the Event Horizon telescope actually imaged a black hole. This was fantastic news. And you can actually see it here. You can read a lot of this for yourself. But this is actually it's actually the shadow of a black hole, and then this is not the event horizon, but the asymmetric ring accretion disk here. And then you can see movement. And I just checked space weather today, and they saw even more movement in M87. So check that out for the latest on that. And then our own Milky Way galaxy has a black hole too, Sagittarius A. It's right near M6 and Lambda Scorpii. And notice it's the one in M87's a monster. Here's ours, Sagittarius A, and it'll fit in here in M87. Look at that. So M87 is a monster. And that's the elliptical galaxy in Virgo. And then black holes, this is theoretical, the negative Schwarzschild solution. And if you can see this, oh, wait. Okay, if you see this, a white hole is space-time is from one end of the sheet to another. A wormhole is if you could bend space-time, that's the Einstein-Rosen bridge, and go from one end to the next, see? Instead of traveling all this distance, it's like a shortcut like that. But it's all theoretical, and you know, white holes really don't exist. But science fiction writers love white holes, go from one end of the galaxy to the next to a white hole, you know. So, and then general relativity predicted gravity waves, and these have been detected. This was the LIGO. There's two of them, and this is how an interferometer works. You can read this for yourself, but they actually detected in September 14, 2015. And then they were only a few 7 milliseconds apart. Isn't that neat? And now there's several of them here. And as of June 2025, 96 mergers have been detected. So now we know about gravity waves. And there's actually two types of gravity waves I found out. The ones detected by LIGO are high-pitched gravity waves. There's also low-frequency gravity waves. So I heard a lecture on this, and the speaker gave a nice analogy. It's like the LIGO ones that we detected are like a piccolo in an orchestra, whereas these would be a tuba. Okay, so this is still experimental, but you can use millisecond pulsar arrays. Neutron stars emit pulsations very regularly, and so we can map the space-time around it. And this is what's being done now to create a background. So if a gravity wave were to come here, it would interrupt these signals, and then that would confirm that a gravity wave came through. See that low frequency one? So a low frequency one hasn't been detected yet. This is still in the works, but this is the basic idea of it, okay? And then here Einstein added lambda, the gravitational constant, because at the time they thought the universe wasn't expanding. Einstein's equation stated that universe was expanding, and so he put this lambda here so that he could stop the expansion of the universe, and called it his greatest blunder. But you know what? Now scientists have discovered, dark energy is actually accelerating the expansion of the universe. So he called it his greatest blunder. But now they're using lambda in Einstein's equations to explain dark energy. So isn't that cool? So Einstein was right again. And then in 28, he begins pursuing the idea of unifying all the forces together. And at the time, with Einstein, only electromagnetism and gravity were the two known forces. Now we know we have the strong, the weak, the electromagnetic, and gravity. So actually, the two forces, the electromagnetic and the weak, have actually been unified, and that was a Nobel Prize winning thing. But the strong and and the strong and gravity have not yet. See, so Einstein was once again ahead of his time because he was trying to unify all the known forces. And here he is riding a bike. He never learned to drive a car. And if you ever watch The Big Bang Theory, the TV series, Sheldon never learned to drive either. He always had Leonard or Penny or somebody drive him, see? So that's where he got the idea from, because Einstein never learned to drive a car. And then he died in April 18, 1955 of abdominal aortic aneurysm. This is how his desk looked. I love some of these famous quotes. I love this one. Politics is for the moment, and equation is for eternity. So if you ever argue politics, just say It's for the moment. An equation is for eternity. God does not play dice. That's that he didn't like quantum mechanics, which is a whole other topic. And this is what I tried to do with this lecture. Everything should be made as simple as possible, but not simpler. I live by that philosophy. I tried to make this as simple as possible, but not simpler. Okay, imagination is more important than knowledge. That's why Hilbert didn't come up with curvature of space time. He just did the math once he heard lectures from Einstein, and then I love this one. Education is what remains when one has forgotten everything they learned in school. I love this because it's so true. I mean, could you sit back on a calculus exam that you had, unless you do math all the time? No, you'd have to really review it and all that. But the fact that you went through it and learned to think that way means you're educated. So education is what remains after you forget everything you learned in school. And he did all the math himself, and you saw that equation. That's a pretty complicated equation, okay? It's not simple algebra. So he was not a dummy in math. He was very good in math. Okay, and then that's basically it. Parting words of wisdom. So sorry for going fast to the end, but you want to. So any questions on any of the black hole stuff, the LIGO, the gravitational waves? I know I went through that quickly, but that's just confirmation of the general theory of relativity. But
My apologies. I'm sorry. You really wanted to take your time with this, and
yeah, I did. I wanted to really, but I had to. The stuff at the end was not explaining the concepts; was just proving what he did was right, technologically and all that, with the Event Horizon Telescope, the LIGO, interferometers, all that stuff. But I went through that quickly. But any questions? So general relativity, curvature of space time, more gravity, time goes slower. Okay, and that's kind of the gist of general relativity. Curves, light is curved in because space-time is curved, so it follows the straightest path it can. It's called the geodesic. I said that there, but so it goes straight, but since space-time is curved, that curves too. That's why you get the arcs and all that, and the Einstein cross and the galaxies when you have a huge area of galaxies, and there's other galaxies behind it, acts as a lens. So, but anything you can add, Eric? What are your parting words of wisdom?
Your presentation, I don't want to blank on you. I guess the only thing that jumped out at me is something I would add is to beware of all the fuss about singularities in the center of black holes. Um, Remember that if you traveled to the very exact North Pole on Earth, you are also arriving at a singularity of sorts, because if you are at the most North Pole on Earth and I say, we'll go north, which way is north? You'll get frustrated.
true.
Right. Or my wife just said, wait until the magnetic pole switch. But no, I'm talking about like latitude, longitude. Like you're running into the limit of the grid coordinate system. And so similarly, the singularity in the black hole, it may not be correct to think of that as a physical thing. It may be more accurate to think of it as you have reached the limits of our mathematical description of
Right.
what's going on
That's what.
there.
Yeah, you're right. You're right.
Or it might
That's
be a physical thing because we're not quite sure yet.
yeah.
And it
Yeah,
might be
you're
more
right.
of a
That's
when than a
basically
where.
where the mathematics, Roger Penrose said that. That's where the mathematics breaks down, and you can't, at the
Yeah.
singularity.
Yeah, thanks, Greg. And Eric, I've just always been fascinated, having always been interested in black holes and quasars since the 60s, 70s. This idea that, okay, I can picture the rubber sheet with the heavy weight, and so
Yeah.
space-time's curved, and the whole, thing about the, Mercury precession of that proving it. But the idea of other things happening with gravitational waves is just Yeah, very cool. If the idea of, if it's like a rubber sheet, now it's waving and the
Yeah,
waves are going along. And so,
yeah.
if that was severe enough, would we feel it go by?
Well, they're traveling at the speed of light too. That's the other
Yeah,
thing. Not
that's
now.
true.
We never feel it going by. I mean, they've gone
Yeah,
by 95 times so
yeah,
far.
I mean,
We
and many,
haven't
many,
felt
many
anything.
more times before LIGO and the
And
other
and
ones
if
could
you
measure
look
it.
at the accuracy of this thing, look, it's so sensitive it can detect a change smaller than 1/10,000th the width of a proton, which is
Wow.
10 to the
Yeah,
negative 19 meters. So 1/10,000th the width of a proton. So that's how sensitive this
you're
thing
not going
needs
to
to
feel
be.
that. Yeah,
Yeah, you're not going to feel that exactly.
yeah,
I'm a
it's still
sensitive
pretty
boy.
neat.
I just know that at one toss per second, I've got pens sticking in my head, all over my body, and welts from baseballs. That's all I got to say.
Yeah. So I sent this to Chris. So if you want, send it out to everyone in the club and now look it over again. And now that you heard me bring it to life, it'll probably make more sense when read
Yeah,
it through
I'll,
now. You know what I mean?
I'll put it up in the files section, Greg.
Okay.
Yeah,
Yeah, on Groups IO.
Yes.
yeah, yeah, I will.
Yeah.
I was going to say, I've got that factor that the time dilation, the length, and the mass. Unless I'm mistaken, that's the Lorentz factor.
Lorentz
And
contraction. Yeah. The Lorentz contraction, it almost got there. Yeah. Lorentz noticed that during the Michelson-Morley experiment when they did, which I left out completely because it's just too. Eric knows about that, but yeah.
I've got a spreadsheet in case anybody just wants a useless thought experiment. I've got a spreadsheet where you can that I put together where you can plug in the speed at which something's going and the length the length of time that it's traveling, and
Oh, good.
it'll factor in the how far the time dilation and all the different dilations. So you
Oh,
plug in like a baseball pitch, and
right.
it'll tell you how far into the future the baseball travels. Or something a little more practical, like an astronaut on the ISS that's up there for 6 months. His dilation parameters compared to somebody on Earth.
Oh,
But the dilation is, it's real. It happens.
yeah.
Your feet are closer to the center of gravity than your head is. So
Yeah,
your
that's
feet,
spaghettification,
you
the
know,
tidal
your
force.
feet end up, aging slower than your head does. It's that granular. It is a fascinating subject.
Oh, yeah, it is. The concepts are difficult to really wrap your head around, but they're actually not that bad if you just remember,
Yeah.
what I said: special relativity, uniform state of motion, flat space time, time slows down, length contracts, and mass increases in the direction of motion when you measure someone else's relative to you moving faster, and then curve mass and energy curve space time, and light tries to go the straightest line possible, but in a curved space time it curves too, and then it produces gravity waves. That's the basic gist of it. I said very few things. I just kind of said them over and over and gave examples and tried to Eric's laughing and tried to drill the point home, right? So
I had a question. Did you
yes.
uh, did you mention anything about Lorentz equations or Lorentz
No, no, no,
transformation?
because it's too confusing. Because
Yeah,
Lorentz didn't have the exact,
he
I
didn't
think, length
understand what his
contraction.
equations were doing, and then Einstein ended up
Yeah, Einstein kind of
producing
used
them.
them. Yeah, that was, I believe, from the Michelson-Morley experiment that
Yeah.
they saw the contraction in the interferometer. Yeah, but and because there was no ether, and that proved that there was no ether, and light didn't need the ether to travel through; it could travel through empty space. So that was an important finding, but it just adds more confusion and more slides. So.
One thing I'll
So,
toss
so
in as a follow-up to the thing before this, which is I bumped in somewhere that the center of the Earth, due to the gravitational time dilation, is about two-ish, you have to fact check me on this, around two-ish years younger than the surface of the Earth.
That's
Not in terms
interesting.
of like geology or anything like that, just like two fewer years have passed for the stuff in the center of the Earth from our perspective up
Oh,
here on the
that's
surface,
interesting.
just due to gravitational effects. But it also shows you the Earth is not huge, but it's also not tiny. And for, 4.5 billion, 5-ish billion years, the total effect now adds up to 2 whole years. Shows you how small the effect is in all but the most extreme circumstances.
Thank you, Greg.
All right.
Yeah, thank
So,
you very
Eric, we'll
much.
give this to Silvera, this talk, and we'll do it
Uh,
again. It'll be fun.
well, now I have. So, Greg, do you mind if I out you a little bit?
What?
Greg sent me an email last night saying, "Hey, I'd love it if you can come to the talk and be ready for some questions." So I apologize that I was utterly unprepared.
No, you were not prepared. I
It was
mean,
great, Eric.
yeah,
Perfect
thank you.
way of distillation for a more complex topic. I wish we just had more members here to experience it.